Okay, back to, we need to show that r dot v cross h is the magnitude of h squared. Okay, and so to do that, we're going to use the fact that we just proved that we can sort of reorder this dot cross product combo. And so by using this, that means the r dot v cross h is in fact the same as taking r cross v and taking that result and dotting that with h. Okay? Now, when we initially worked with r cross v, and in fact that's how we defined h, right? That was the original definition of h. And so we're going to plug that in for here, and that, of course, just means we get h dot h, right? Well, what is h dot h? H dot h is the magnitude of h squared. So in fact, we've proven that. Okay. So now what we'll do with this is, we've got this form here, but we also came up with earlier this version of r dot v cross h. So that means all of this stuff is also equal to the magnitude of h squared. Okay, so we've got h squared equals this stuff. In fact, let me replace the magnitude of vector r with, in fact, magnitude of r is r, right? So both these terms have r in it, so we'll factor this r out, and we're left with gm plus the magnitude of that constant vector c times the cosine of theta. And that's equal to magnitude of h squared. So solving this for r is going to be the magnitude of vector h squared over g times m plus the magnitude of vector c times the cosine of theta. And I'm going to take that on just a little bit of a rewrite again. So I'm going to, just a second here. Okay, we're going to factor out of the denominator a gm, so it reads 1 plus the magnitude of c over gm times the cosine of theta. A little odd, I know. And then on the numerator we still have this magnitude of vector h squared. And in fact, I'm going to rewrite it as two separate fractions that way. And then I'm going to define some couple of things here. I'm going to let E be the magnitude of vector c over gm. All right. And we're going to let D be the magnitude of vector h squared over the magnitude of vector c. Okay. Now, by doing this, note that this part in here, that just becomes the E. And this part here is actually E times D, right? So we can write the whole final thing then, R is equal to E times D divided by 1 plus E times the cosine of theta. Now, I claim what we have here is a big deal. R equals ED times 1 plus E cosine theta. This is sort of the happy end of this lecture. You may say, well, wait a minute, that hasn't shown we have an elliptical orbit. And I claim it does. But I'm leaving a little bit to you, and this will be your assignment in special problems. You're going to have to show that, in fact, that is the equation of an ellipse in polar coordinates. So, thanks for watching. Enjoy your proof.